We are about to begin our study of the universe, our galaxy, our solar system. In other words, we are beginning the study of astronomy. To study astronomy, we first need to understand waves, because we use waves in order to understand what is in our universe. Waves are the movement of energy. There are two groups of waves: mechanical waves and electromagnetic waves. Mechanical waves move energy only within a medium. When we talk about a medium is matter, whether it be a solid, a liquid, or a gas. So mechanical waves can only move through matter. There are two types of mechanical waves. The first is a transverse wave. An example of a transverse wave is a water wave. And the second type of mechanical wave is a compressional or a longitudinal wave. An example of a longitudinal or compressional wave are sound waves. A transverse wave is a wave like a water wave that goes up and down. It has peaks, which are called crests, and in valleys, which are called troughs. And we measure a transverse wave by its wavelength from one trough to the next trough, or from one crest to the next crest. A compressional wave, or a longitudinal wave, moves back and forth like a slinky. And sometimes it's pushed together or compressed, and then there's other places where it's expanded. This is also called rarefaction. Rarefaction. This is the expansion. Electromagnetic waves are the waves that will be important to us in the study of astronomy. Electromagnetic waves do not require a medium. They can travel through space. All electromagnetic waves travel at the speed of light, which is 300,000 kilometers per second, or 186,000 miles per second. They can travel through empty space, and they can actually also travel through some mediums. Different ones will travel through different mediums. These waves are the waves of the electromagnetic spectrum, including from short to long wavelength. They are gamma waves, X-rays, ultraviolet, visible light, infrared, microwaves, and radio waves. Electromagnetic waves come in very different lengths. As we look at the electromagnetic spectrum, from gamma rays, way down here on this end of the spectrum, gamma rays are measured in angstroms or nanometers. An angstrom is 1/10,000,000th of a meter. These waves are so tiny, the length of the wave is about the size of an atom. As we move across, we get over here to in the ultraviolet region. These waves are measured. They're about the size of a molecule, several atoms that are connected together. We get into visible light. Visible light waves can be compared to the length, the size of a cell in your body. A human cell would be about the length of a visible light wave. Notice that visible light goes from 700 nanometers to about 400 nanometers, a very small part of the electromagnetic spectrum is what's picked up with your eyes. As we move on into infrared and microwaves, these waves are still very small, the width of a human hair up to the width of a pin. And then we get into the radio waves. And radio waves can start out about the width of your hand, but radio waves can also be as long as several kilometers in length, the wavelength. So there's a very large spectrum of the electromagnetic spectrum as far as wavelengths. So let's talk about the parts of a wave for a minute. All waves of the electromagnetic spectrum are transverse waves. And the transverse wave is similar to what you know as a water wave. It goes up and down. It has crests, which are the high points of the wave, and it has troughs, which are low points of the wave. And right down the middle is what is called the rest position, or the equilibrium. This is, if we flatten the wave out, it would create a straight line, and that's the line right down the middle of the wave. Of course, the wavelength is the distance between one crest and the next crest. That's the wavelength. Or from one trough to the very next trough will be the same distance. The amplitude of the wave is the distance from the rest position to the bottom of the trough, or from the rest position to the top of the crest. The greater the amplitude, the more energy the wave has. So amplitude deals with the amount of energy that's carried by the wave. And the last thing is frequency. Frequency of the wave is, as the wave moves, how many crests pass a certain point in a given amount of time. We can also measure the same thing with the troughs. How many troughs pass a certain point in a given time. That is the frequency. Different wavelengths will, moving at the same speed, like the speed of light, will have different frequencies because the wavelength is different. So gamma rays will have a greater frequency than radio waves would. So let's remember that high frequency waves will have shorter wavelengths. More crests or troughs will pass a certain position in a given amount of time, and longer wavelengths have low frequency. They have fewer crests or fewer troughs will pass that same point in the same amount of time. High frequency waves generally have more energy than low frequency waves. And in the electromagnetic spectrum, gamma rays, which are very high frequency, are very energetic and are very dangerous. We do not want to be exposed to gamma rays or X-rays or even ultraviolet to a great extent. But radio waves and such as that have low frequency and less energy and are not considered dangerous to us. So that's our study of waves today, and our next lesson will be going further into looking at the universe and astronomy.